Good afternoon, everyone. It is my great pleasure to be able to present you a work which was a collaboration between me and my dear colleagues, Mr. Jacimovic and Mr. Stanic. We all work at the Institute for Environmental and Hydraulical Engineering at the University of Belgrade. This work is actually a part of a bigger project. It is a project funded by the Serbian Ministry of Science. It deals with the urban drainage systems as key infrastructures in towns and cities. I will give you just an outline of the presentation. First, I will give you some of the reasons why we got interested in this topic. Then I'll present our research goals and expectations, explain how we developed the model, which will I present, then give some results, and of course some conclusions. Most of what we were talking today and, well, yesterday is how valuable groundwater as a resource is. It is one of the major sources of potable water. By 2050, it is estimated that the population on planet Earth will be 10 billion people, which will present an even greater stress to an already stressed resource. Now, in trying to apply some sustainable strategies of groundwater management needs a good assessment tool of the groundwater status. Regional groundwater models, or at a larger scale maybe distributed hydrological models, can provide a good basis for analyzing different scenarios. These models do rely on a large number of parameters, one of which is the infiltration. Infiltration happens in the uppermost layer of the soil. It is a transition from the unsaturated to saturated flow. It is also a connection between surface and groundwater. It is, well, the crucial, I would say, the crucial quantity of water which connects the surface and groundwater. But however, in most of the models, it is not an input parameter, but rather a calibration parameter. The reason for so is very simple. It is of complex nature, so people just have a hard time estimating it. Now, as Mr. William Kling said yesterday, the planet is making a shift from a rural to an urban lifestyle. We have a lot of urbanization, problems related to urbanization. We have an increased runoff. We have changes in the groundwater regime. We try to relieve the stress of urbanization on the aquifers by using the urban stormwater systems. But however, these systems do require detailed insight into the unsaturated, saturated vertical flow. On the other hand, we have a lot of field observations that show a high heterogeneity in the soil material. We have here a picture of the granulometric curve in the aquitard of Belgrade. This variation has inspired for the past decades, a lot of researchers to work on new groundwater theories in a probabilistic framework. But unfortunately, these theories are for now limited to horizontal and saturated flow. So, having to deal with the urban stormwater systems, we need better insight to the Vadose zone infiltration. So an attempt was made to create a model under probabilistic framework. This 1D vertical numerical model was used to analyze the long-term infiltration process and to evaluate the effects of aquitard heterogeneity on the annual recharge intensity of the aquifer. Now, the model it uses meteorological data, including daily precipitation data, to estimate the potential evapotranspiration using the standard Penman-Montate model. For the soil constitutive relations, we use the Van Genuchten equations. This soil description is altered in the model to simulate heterogeneities in a process which I will later explain. Now, regarding water dynamics, we use the Richards equation. And finally, as a result, we get infiltration at a certain depth. Now, some insight to the soil model. Well, the Van Genuchten equations include relations between the water content and pressure heads, which you can see on the left side, and relative hydraulic conductivity, and again pressure head on the right side. This is the typical shape of the curves. However, knowing that the soil material is very heterogenic, which the field investigations have shown, we also observed that, well, not just us, but most of the researchers, that the variations are following some pattern. Actually, the hydraulic conductivity and porosity follow a log normal distribution in space. In this type of analysis, those quantities are usually considered to be stationary, meaning that they do not change in time. Now, having these distribution parameters, the mean and the standard deviation of the distribution, we can try to recreate the natural heterogeneity using the statistical methods. Now, here on the left, in the left corner, we have a usual soil model that is with the constant value of saturated hydraulic conductivity, shown here by uniform color. What we try to do is, by using statistical methods, to create a heterogenic model, here shown in the center, with hydraulic conductivities generated by statistical methods, and eventually to find the hydraulical equivalent of that heterogenic model in a homogenic model. That is to find like equivalent hydraulic conductivity. Now, how we do the hydraulic conductivity field, we take the mean and the standard variation of the saturated hydraulic conductivity and generate this random field. The parameter P here is a random number that is the probability that the value of saturated hydraulic conductivity is K. But knowing that this is not a completely random field, there exists some spatial correlation. We also introduced the correlation coefficient in this way, where the coefficient is a function of h, which is the distance between points, and L, the correlation scale. The correlation scale is a parameter that has to be determined in the field. Now, having these two, we use the Eman-Conover method to induce the correlation to a random field, and finally to get what we wanted, that is a heterogeneous sample with a heterogeneous sample. Well, actually, we get a lot of samples because we get a lot of samples which we then use the Monte Carlo simulations to evaluate the result of each of them. For the water dynamics, that is the Richards equation, the discretization techniques for space and time are stated here. There was no particular difference between finite element and finite difference methods. And the hydraulic conductivity estimate at the cell front is as shown. Now, the experimental soil is the Belgrade soil aquitard with its parameters given in the table. The correlation scale is assumed to be 1 meter. That means that at a depth of 3 meters there exists no significant correlation. The distribution is log normal and the standard deviation is 1.0. That is 1 order of the magnitude of the hydraulic conductivity. Now for the calculation, we do calculate the infiltration at the depth of 2 meters. We use equidistant nodes. At the At the upper boundary, there is the net flux, that is the rainfall minus the evapotranspiration. At the bottom boundary, we put the free drainage, and the initial water content is the field capacity. The rainfall data we took for the 2009 year for the station of Belgrade, that was not, it was just a normal year without any particular extremes. The total rainfall for the year is 804.4 millimeters. And here are some of the results. Well, using the heterogenic sample, we did 200 calculations with and this here, the bottom graph shows the results we got. Here on the vertical scale, on the vertical axis, we have infiltration, total infiltration at a depth of 2 meters, and on the horizontal scale we have time, where 1 represents January, 2 represents February, and so on. These results. These 200 samples that we calculated gave us rather different results. So the red dots represent the mean value of all the results. We can see that after a year, the mean total infiltration at 2 meters is around 100 millimeters, which is around 12% of the total rainfall. Now, what was surprising was how large variability of the results was. The standard deviation of the results is of magnitude of the mean value. What was even more surprising were the extreme values. The minimum infiltration was 0, while the maximum infiltration was going up to 320 millimeters per year, which is more than 40% of total rainfall. Then we compared the 3 models. First, the standard model, the ones that is used. Second, our model, and third, a model which is hydraulically equivalent homogeneous model to this heterogenic model. Blue triangles show the results of the standard model, red dots show our model, and green boxes show this K equivalent. We see that the heterogenic sample and its hydraulic equivalent sample do have very similar results. However, these results are almost 1/2 of what we get with the standard model. Now, the conclusions that we got, I stated some of them. Well, we did expect to get a lot of variations, but we were surprised by how large the variations were. Which model is right still has to be determined in the field. That is our future work. We are currently setting up an experimental polygon, an urban watershed in our backyard, where we will take samples at every 30 centimeters of sample of the soil to estimate soil parameters and find the actual correlation scale. Now, this urban watershed drains to this green area where we plan to put, well, to analyze a couple of stormwater systems, urban stormwater systems. And we will also include, this is under construction, a meteorological station just to follow all the meteorological data at the site. Well, thank you for your attention.